so today we are going to be doing our presentation on John Griggs Thompson. So my name is Megan Brown.
I'm Nusha.
And I'm Darshaya. John Griggs Thompson was born October 13, 1932. He is actually still alive today. He is 87 right now. He received his bachelor's degree at Yale University in 1955 and completed his education by getting his doctorate at the University of Chicago in 1959. Thompson became an assistant at Harvard University in 1961 until 1962, when he was appointed a professor at the University of Chicago. Now we are getting on to the good stuff. I think it is important to note here that John Thompson's work focused mainly on group theory, also that it was our first time diving into mathematical category. Thompson published a paper with Walter Fiat on solvability of groups of odd order. We will talk about it a little later. He accepted a fellowship in 1968 at the University College in Cambridge. He has received many awards for his work. It continues on with the Fields Medal in 1970. He was appointed to the Rose Ball Professorship of Pure Mathematics at Cambridge. Some other important awards were his Wolf Prize and Poincaré Prize, which he received in the same year of 1992, and his ABEL Prize awarded in 2008 along with his partner Jacques Tix. As we can see here, he is now a professor at the University of Cambridge and Florida. One more thing to know is that he received honorary degrees from the universities Yale in 1980, Chicago in 1985, Oxford in 1987, and Ohio State in 2008. I would like to have a look through an overview of the work he has won awards for. All medals and prizes that he won were for his contributions to algebra or finite group theory. Specifically, Thompson's thesis solved the long-standing conjecture reaching back to work of Frobenius that remained unsolved for 60 years. He went on to work on the classification of the finite simple groups. Thompson and Walter Fiat worked together on the proof that a finite non-abelian simple group must have an even order. This is the same theorem that we introduced in the last slide. John Thompson's work is new and exciting. Even the Wolf Foundation states, the penetrating power of Thompson's genius is astonishing. His contributions to group theory and related subjects are of enduring significance. I have to say, I agree with them. John Griggs Thompson and Walter Fiat won a Fields Medal for their work on group theory. Group theory, which for us was the first time hearing about this subject, is a study of the science of symmetries. All non-cyclic finite simple groups have an even order. This was determined further by Thompson, that the minimal simple finite groups, that is, the simple finite groups whose proper subgroups are solvable. This classification is helpful because it produces a characterization of each simple group. Let's look at some of the terms from the theorem. Here we have the cyclic groups with 1, 2, 3, and 5 elements. There are infinitely many more options. Here we have non-cyclic groups. The best way I can describe it is a group that is generated with more than one group. Or it can be a summation of cyclic groups, for example, something like this, or this, or this, or a summation of all of them. And this can have infinite examples.
Algebraically, a group is cyclic if it has an element that is a generator, which means when the group operation is applied to this generator multiple times, it creates all the elements in the group. As an example of a cyclic, I have picked a Z6, which has an addition operation, and it is of order 6. Now, if you look at all the elements, they generate subgroups. And with applying the addition, meaning adding all those elements multiple times to itself, we will get the subgroups that are in pink. Now, only 1 and 5 generate a subgroup that is equivalent to Z6 itself. Therefore, those are the generators, and this group is cyclic. For an example of non-cyclic, I have picked UN, a unity group, which is a group of integers that are co-prime to n. So over here, U8, we have 3, 5, 1, 3, 5, and 7 co-prime to 8. And the order of this group is 4. Now, all of these elements generate subgroups that are, none of these subgroups are equal to U8. Therefore, this is a non-cyclic finite simple group of an even order. How is it that every finite group of odd order implies that every finite simple group has even orders unless it is a cyclic prime? Over here, we'll use a different definition for solvable than our previous presentation. A finite group is solvable if it has a composition series, all of whose factors are cyclic groups of prime orders, similar to prime factorization, whereas here it's based on group compositions. We also need to note that simple groups have no subgroups other than themselves and the identity. Therefore, if when we say every finite group of odd order, we can divide this to two cases. Case one is it can be a cyclic group of prime order that is trivially composable to identity in itself, which means that it's simple. And case two is that, or it can be written as a composition of groups of prime orders, which means that this is not simple. From these two cases, in other words, based on this definition, if a group is finite and simple, and if it is odd, then it can be only from case one, which is cyclic primes. Otherwise, it must be even.
Now we shall look at simple groups, which is the building blocks of finite groups. G is a simple group if and only if its normal subgroups are one element and the group being G, so the whole group itself. And the order of the group has to do with the number of elements in it. Assume n is the order of the group. If you take an element who is a generator of the group and you do the group operation n times to that generator, you will get the identity element. Thompson determined the minimal simple finite groups. This is to say the simple finite groups whose proper subgroups are solvable. This is the first substantial result achieved concerning simple groups. Another reason why this classification is helpful is because it produces a characterization of each simple group. Another important thing to note is that the proof was 255 pages long, which started a wave of other authors writing long proofs. We read through, well, more like skimmed through the book. The first 3 chapters were on explaining mathematical symbols and jargon. Theorems and lemmas were stated so that they may be used to be recalled from. The official proof doesn't start until the 4th chapter and ends in the 6th and final chapter. It had a few small, easier explanations in the beginnings of chapter 4 of what was to come, but the rest was all really hard to follow. It was almost like it used its own language.
As stated before, John G. Thompson had received the Wolf Prize in the year of 1992, and he received his prize for his profound contributions to all aspects of finite group theory and connections with the branches of mathematics. For the Wolf Prize, we have this theorem that says if a finite group has a fixed point-free automorphism of finite order, then the group is nilpotent. What do the terms in the statement mean? Automorphism is simply a bijective homomorphism. A group homomorphism is a function h such that for all u and v in G, it holds that h of u product v equals h of u product h of v. The product here is the group operation. An automorphism of a group is termed fixed point free if the only element of the group that is fixed under the action of automorphism is the identity element. And nilpotent is basically a measure of how abelian a group is. How can nilpotent determine how abelian a group is? It uses commutators. And as you can see in the slide, commutators is the function of the square brackets that takes g and x from a group, and it is equal to g squared x squared gx. Now here, if g and x commute, then the commutator equals to the identity. In an abelian group, everything commutes, which means that every commutator equals to the identity element. Therefore, an abelian group is nilpotent of class 1. It is the most nilpotent or abelian it can get. Nilpotent of higher classes, like of order n, is if we take the commutator n times and we get to the identity. For an example, I have put an example for nilpotent of class 2, and I've defined a function based on g and x, where g is a fixed element in the group and x is any other element. And if this function we apply it twice, and the product of it equals to the identity, then this group is nilpotent of class 2. To find group nilpotent, we can use upper central series that is constructed from higher order generalization of the center. And the center is the set of elements that commute with everything in the group. The length of this upper central series determines what class of nilpotent the group is.
The Norwegian Academy of Science and Letters decided to award the ABEL Prize to John Griggs, Thompson, and Jack Titt in 2008 for the classification of finite simple groups. Finite groups are used in mathematical concepts like permutations and linear groups, which are made up of symmetries. Thompson revolutionized the theory of finite groups by proving deep theorems that laid the foundation for the complete classification of finite simple groups. For a long time, the classification on finite simple groups looked very gloomy. Thompson, in a way, came in and saved the day, bringing the concept back into the light, where many other mathematicians would follow and make their own contributions based off of his work. Thompson is referred to as the world's leading group theorist. His name is forever tied to the huge classification project, or the 30-year war, as Daniel Gorenstein called it, between 1950s and 1980s. But the highlight is the Fiat-Thompson theorem proved in 1963, which is that every non-elementary simple group has even number of elements. Equivalently, every finite group of odd order is soluble. Thompson also worked on theorems that gave the classification of n-groups. An n-group is a group whose local subgroups are solvable groups. The non-solvables ones were classified by Thompson during his work on finding all the minimal finite simple groups. Now, although the dream of the classification of finite simple groups goes back to at least the 1890s, at this time, Lagrange, Gauss, and their contemporaries were familiar with the cyclic groups of all positive integers and alternating groups. Galois, who gave us the term group and the concept, a normal subgroup, was also familiar with the fractional linear groups and their connection to p-division points on elliptic curves. In 1896, Dedekind invited Frobenius to consider the problem of factoring the group determinant of a finite non-abelian group. Frobenius' determinant theorem was the birth of the theory of group characters. The early work of Fiat, Suzuki, and Thompson dealt exclusively with groups whose local subgroups H were solvable, thus for which E of H is equal to 1. It was Gorenstein and Walter in the mid-1960s who first came to grips with the general problem of simple groups with non-solvable local subgroups. Gorenstein provided in 1972 a 16-step plan for the completion of the classification proof. The pace of the classification before this kind was really sad. Not a single leading group theorist besides Gorenstein in 1972 believed that the classification would be completed this century. By 1976, almost everyone believed that the classification problem was busted.
Classification of finite simple groups was like finding prime numbers in group theory. Like prime numbers, the simple groups are the atoms of group theory. They form the building blocks for all other groups. Classifying all finite simple groups was complicated. Most could be classified simply into cyclic groups of prime order. However, there were some large groups that did not fit into these obvious patterns, called the sporadic groups. There are exactly 26 of them, and it took decades to find them all. Thompson contributed in finding some of these sporadic groups. The first 5 of these groups were found in an early stage of group theory, namely by Emil Matthew in 1860s. Matthew's groups were not particularly big, and comparing to other groups, it was very small. The largest sporadic group was named the Monster by John Conway. The Monster was created by Fisher and Grease, also known as the Friendly Giant. The order of the Monster is this very big number that you can see on the slide. The Monster group contains the Baby Monster group and 20 sporadic groups, including itself as subquotients.
One of the sporadic groups groups got its name after John Thompson. It's called the Thompson groupa, abbreviated TH. The order of this is stated here, which is also relatively small compared to the monster. Its almost incredible conclusion is that all finite simple groups belong to certain standard families, except for the 26 sporadic groups. Thompson and his students played a major role in understanding the properties of these sporadic groups, including the largest, the monster. The completed proof of the classification was announced after two mathematicians published a 1,221-page proof for the missing quasi-thin case. Daniel Gorenstein steered the classification into a successful conclusion in 1981. Some things to note before we define the groups is that in 1947, Zassenhaus hoped to linearize the classification process by identifying all simple groups as groups of automorphisms of some linear structure. In 1957, Suzuki looked at the non-existence of non-abelian simple CA groups of odd order, which was the first breakthrough in the direction of Miller-Burnside odd-order conjecture. Nevertheless, difficulties still seemed insurmountable. The next theorem that affected the classification was Thompson's thesis completed between 1959 to 1960. Another thing to note in the classification of finite simple groups is the existence of minimal groups. Some important definitions here will be the weak closure and Thompson subgroup, the first and second definitions respectively on the slides. In 1958, Hall and Thompson extended Suzuki's theorem on CA groups of odd order to the nilpotent centralizer case, where Fiat improved character theory. Fiat and Thompson did a collaboration on the odd order theorem in 1963, which worked on minimal simple groups of even order, stated here for clarity. I thought this last definition here was interesting because when we did our research on groups, simple groups were explained in this manner. The simple groups are between P rank 2 and 3. Brouwer came up with a two-step strategy for proving the classification theorem. 1. Determine all possible structures for an involution centralizer in a finite simple group. 2. For each possible structure, determine all finite simple groups with such an involution centralizer. Brouwer had proved some sample cases for step 2, but no one had any idea on how to do step 1. Theorem. If every finite simple group is isomorphic to one of the following groups. Now, we have already talked about cyclic groups. The alternating groups of degree at least 5 is explained as groups of Lie types over the field with one element, which unites this family with the next, and thus all families of non-abelian finite simple groups may be considered to be Lie type. An alternating group is the group of even permutations of a finite set. The alternating group on a set of n elements is called the alternating group of degree n, or the alternating group of on n letters and denoted by an. Lie-type groups has a close relationship with the Lie groups, since a compact Lie group may be viewed as the rational points of a reductive linear algebraic group over the field of real numbers. Lie groups are a group whose elements are organized continuously and smoothly, as opposed to discrete groups, where the elements are separated. This makes Lie groups differentiable manifolds. Also known as the theory of continuous transformation groups, sporadic groups are exactly as they sound, sporadic. They can be explained as not like any of other groups, but similar to Tit's groups, but not as similar to groups of Lie type, but also not. I feel like the best way to describe it is through the monster that we had recently seen as the largest sporadic group, contained all but 6 of the other sporadic groups as subgroups. Tit's groups is not strictly a group of Lie type. It is sometimes regarded as the 27th sporadic group found by Jacques Tits. The Tits group is one of simple n groups that was overlooked in Thompson's first announcement of the classification of simple n groups, as it had not been discovered at the time. It also one of the thin finite groups.
Okay, it is 1:30.
Quite a bit of recent research in finite group theory has developed in response to problems from other areas of mathematics. For example, field theory, model theory, graph theory, and finite geometry. Many of these problems have been around for quite a while, but suddenly became accessible thanks to the completion of the classification of finite simple groups, which was one of the greatest achievements in the 20th century. Thompson's achievements are of great depth and influence, and ultimately are the backbone of modern group theory.